So good afternoon, everyone. My name is Hao Zheng. I'm assistant professor at ECE department. So first of all, thank the committee for organizing the virtual seminars as usual. The title of my today's presentation is Efficient Computer Architectures for AI ML Computing. So as usual, a few words about myself. I joined UCF in 2021, and I'm leading Intelligent Computer Architecture and Technology Laboratory. We have 3 PhD students and 2 undergraduate research assistants at this moment. So my research falls into the broad area of computer architecture. Specifically, I'm focusing on the machine learning for efficient computing. In other words, we are trying to utilize some machine learning algorithms for optimizing current computer system design, for example, the resource management or the power management. And during my PhD, I focused on the network-on-chip design for medical architectures. So for this project, we mainly design a flexible, versatile communication fabrics in support of multi-application execution. So at the UCF, I started a line of research in AI chips for emerging applications such as deep neural network and graph applications, which will be further discussed in the following presentation. So I'm also interested in chiplet-based system design for heterogeneous medical architectures. We are trying to leverage those advanced packaging technology to sustain the performance scaling of current computer systems. So more information could be found at my personal website. If you have any questions, or please feel free to send me an email. So a few slides to describe the general background. So machine learning applications have been applied to every corner of our lives, from economic, science, health, education. Apparently, they are very popular nowadays. But in the meantime, they are posing many computation, memory, and communication challenges on the underlying hardware. So current general purpose processors are not efficient enough to handle those computations. And this motivates the entire society moving towards the domain-specific architectures. So in other words, we have to customize the chips, adapting to a given set of applications, therefore improving the performance and energy efficiencies. So the following projects are pretty are related to this topic. So the first topic, I title it as pursuing parallelism in large-scale deep neural network accelerators. The parallelism is always the key concept, or key methodology to scale the system performance. However, we observe 2 major challenges in designing large-scale deep neural network accelerators. The first challenge is the memory bandwidth. Please imagine if we put tons of those parameters on a single chip, and those data require excessive access to the both off-chip and on-chip buffers. And how do we efficiently manage the memory bandwidth? This is the first challenge. And the second challenge is the data movement. So if we simply scale the chip size with millions or even not millions, so the hundreds of thousands of the processing elements, how do we orchestrate the data movement between those processing elements? So this is the second major challenge. So to better illustrate the problem, I give a toy example here. So this is a typical convolution layer within the DNN models. So if we formulate this problem as an equation to this nested loop with multiple indices, so the most common optimization techniques is we can interchange the order of those indices or loops to reduce the memory access requirements. But which one is the best? So this is the first question, because we have so many models with different, different matrix dimensions. So how do we select the most appropriate data flow, the loop order, to reduce the memory access volume? And the second one, if we choose a combination of those parallelization strategies and map into the chip, and how do we manage the data movement among those processing elements? To address this problem, so we first propose some flexible parallelism strategies for DNN accelerators with the distributed buffers, because the loop orders can alleviate the excessive off-chip memory access. So the distributed buffer is one kind of solution to alleviate the memory bandwidth for the on-chip buffers. and how we propose an algorithm to select them. And the second one, so once we confirm the parallelization strategy and the mapping strategy, and how do we configure those interconnection networks to support the data movement? And this is what we have done for the first project. And the second one is we aim to enable the text level parallelism for DNN acceleration. So the previous project is mainly targeted for the data level parallelism. Actually, there's some dependency between those different layers within one DNN model. Therefore, sometimes the large chip can have some underutilization issues. So that's the reason why we should support multi-application execution to fully utilize those memory computation resources. But the major challenges are the diverse computation and communication demands across different layers, not to mention the different models. And with these different demands, so how do we design a versatile chip to support the different computation communication requirements from different jobs? And second challenge is the resource scheduling, because we have so many different requirements from different applications. To support the simultaneous execution of those different jobs, how do we efficiently allocate those resources to different tasks? And so to address these two major challenges, the first one, we designed a flexible and versatile DNN accelerator supporting the DNN execution. So the key idea is we have a unified accelerators. We can dynamically partition those resources, including the memory, the interconnects, and the processing element to set multiple sub-accelerators. And each of them can be configured as a single type of those accelerators to support a given set of applications. Right. So, and we can support the dynamic allocation. So it comes with another issue. So how do we allocate those resources? So this comes with two challenges, because we should spatially partition the resources among those accelerators. In other ways, for each partition resource, how do we schedule those applications in a time domain? So this motivates us to propose a genetic algorithm-based scheduling policy to enable both temporal and the spatial task allocation with near optimal performance. So we already discussed the DNN inference. So next project, so we did some work on in accelerating the DNN training in the Chiplet-based system via the flexible interconnects. So right now, people mostly focus on how to scale out the system by distributing those DNN training to multiple to multiple computers or the servers. Right, to enable this distribution, so people propose some collective communication libraries such as ARIES or reduce scatter to perform the gradient updates. For example, this is an example of the tree-based or reduced operation. So all those partition data are propagated to its adjacent nodes to perform the accumulation. But the major issue, there's a mismatch between these kind of communication patterns and the physical topologies. Significant amount of those network resources are underutilized. And as such, so we propose, so probably we should scale up the system instead of scale out the system. So we are trying to utilize the silicon interposer to integrate multiple smaller accelerator chips in a single system in one package. And because the silicon interposer can provide more flexibility to reconfigure those interconnection networks, adapting to different all-reduced algorithms. And we also propose some automatic hardware and algorithm co-optimization techniques without changing the original operations. So in other words, if you are using a current existing NVIDIA collective communication library or PyTorch libraries, you don't have to change your original operation. You just run your application, so the rest of the optimization will be done by the hardware. And our preliminary study indicates up to 2 times throughput and latency improvement as compared to the simple design. So the last research project we are doing at the UCF is exploring efficient accelerator designs for graph convolutional neural networks. So the biggest difference between the graph convolution neural network and the traditional convolutional neural network is the sparsity. And the sparsity results from the random connectivity between different vertices. And essentially, it's really hard to predict these connectivities at the wrong time, right? So we formulate this problem as some sparse and dense matrix multiplication. If you look at the matrix, so the sparse matrix adhere to represent the connectivity among different nodes. And the issue is those non-zero elements are randomly unevenly distributed across each row and the column, right? So the first question is, how do we compress the sparse matrix to eliminate those non-zero elements? And there are multiple options at this moment, but which one is the best for what condition? So we conduct some analysis for this part. And the second one is the compression format always comes with some latency overheads because we have to reconstruct the matrix when performing the matrix-matrix multiplication. And how do we efficiently overlap those latency at the hardware level? And the second major challenge is workload imbalance. So to distribute a matrix for the multiplication, so we can either partition each row or each column and distribute them to different processing elements to simultaneously perform the operation. But the issue is the uneven distribution of non-zero elements can cause some processing elements are underutilized. And sorry about that. So is there any better solution to solve this one? Even though people already propose some solutions to optimize the graph convolution neural networks from the data flow point of view or the architecture point of view, but we're still lacking a holistic search or view of the entire GCN design. So we conduct some preliminary study where the result indicate that a holistic search framework can further expand the design search space as compared to the individual optimization techniques. So this motivates us to develop a holistic framework which is compatible with existing PyTorch, TensorFlow, or other computing other libraries. So essentially, we profile some input parameters from the PyTorch or TensorFlow and take them as the input, along with some hardware information, for example, the workload size, tiling size, different compression formats, and hardware parameters. And it comes to our design genetic-based exploration algorithm. And the algorithm based on different optimization objectives. The framework will suggest you the optimal combination of those optimization techniques. So through these optimization techniques, we find some interesting dynamic interactions between the data flow architecture and the sparsity optimization techniques. Name one. So we found the incompatible data flow and the compression format will significantly hurt the performance for the pipelining, which means if you didn't find a suitable data flow or architecture design, and this will hurt the pipeline efficiency. And the framework can also generalize and some optimal solutions, for example, the data flow and the compression formats. So the framework can deliver magnitude of the performance and energy efficiency improvement as compared to existing accelerator designs. So let me conclude my talk with a couple future research directions. The first one is adaptive domain-specific architecture for emerging applications. I will continue my exploration in such area. In the meantime, I'm also interested in exploring the hardware-software optimization for emerging applications such as the general graph applications and the vision transformers or other type of applications. And I'm also interested in the technology-driven system design. For example, the 2.5D, 3D system design, because we still have some challenges in overcoming the limited bandwidth caused by the micro bump design or the via design, TSV design. So how do we design a better communication system from the topology routing point of view? And we are also interested in solving some architecture challenges from integrating advanced technologies in the computing system, say the silicon photonics, wireless interconnects, non-volatile memories, And we're also interested in the resilient AI ML accelerator designs. Actually, we have one project studying the resilience and AI accelerator designs. In particular, we are targeting the transient and permanent faults because current machine learning models always comes with millions or even billions of the parameters. And sometimes, sometimes a few bits data corruption, we call it silent data corruption, can significantly degrade the machine learning performance. And how do we efficiently detect those errors, silent data corruption, and how do we theoretically fundamentally eliminate those data corruption? This is the major research direction. Okay, that's all. Thank you.